Hello everybody, and welcome to my Superfast video, Special Relativity in less than 15 minutes. Very briefly, I want to clarify that the special relativity that we're going to be talking about today deals with high-speed motion. There's also a theory of general relativity that deals with gravity, black holes, curved space-time, and it does include the special theory, but we won't be doing the general theory today. In this video, I'm going to conceptually describe the major effects of Einstein's theory of special relativity in a non-academic and conceptual manner, and in less than 15 minutes. If you want a slower, more detailed presentation, see my playlist for special relativity in less than an hour or so. For relativity experts, we will not be using hyperbolic geometry, as we will be presenting special relativity in a more conceptual and non-academic manner today. Now, we've only got 15 minutes to do this, so let's get going. We begin by assuming that you and I are sitting at a table talking, maybe over dinner. It appears that we are not moving at all in any direction, right? Well, that's how it appears, but that's a deception. That is wrong. We are both, in fact, moving at the speed of light, but it's not through space or one of the three dimensions of space. Rather, we're moving at the speed of light through time. We are aging at the same rate, and 1 second on your wristwatch is also 1 second on my wristwatch as we move through time at the speed of light. It doesn't seem like we're moving because we can't see directly into the time direction like we see into one of the three spatial directions. Now, we live in a universe that consists of 3 dimensions of space and 1 dimension of time, for a total of 4 dimensions of what is called space-time. That's depicted here. This is space-time. In this 4-dimensional universe that we call space-time, we're always moving at the speed of light, as indicated by this vector here. We'll talk about that in a minute. But we're either moving at the speed of light through time or some combination of space and time. But in space-time in 4 dimensions, we're always moving at the speed of light. So let's take a look at a visual representation of this to clarify how it can be. Okay, so we're going to start out here by presenting 2 vectors. A vector is simply a line with an arrow that represents both a magnitude and a direction. In this example, each vector, one for each of us, has a magnitude of 186,000 miles per second, which is the speed of light, because that's how fast we and everything else moves through space-time. No slower, no faster. It's the only speed in the universe in 4 dimensions. Now, both you and I and everything have such a vector associated with us. As shown here, your vector is going to be black and mine's going to be red. Since we are both sitting at a table and not moving through one of the 3 spatial directions, both of our vectors point entirely in the same direction. And 1 second on your watch equals 1 second on my watch. We're both moving through time the same way. We're just a few feet apart. However, in space-time, there's also 3 spatial dimensions we're not showing yet. There's up, down, left, right, forward, back. So I'm going to represent the x direction of space for each of us in another diagram. And let's take a look at that. And we now have a representation of both space and time in one diagram. Each of these coordinate systems shown here represents a 4-dimensional space-time, which is 3 dimensions of space and 1 dimension of time. And note that we both have our own private coordinate system, as also shown here. And as we stated earlier, our vectors are both currently pointed in the direction of time only, directly on the time axis, as we are at rest relative to each other. But now let's see what happens to my vector and our measurements of time, length, and mass if I get in a spaceship and go about 91% or so the speed of light through space, while you remain sitting at the table awaiting my return. Maybe you're expecting me to pay for the meal when the bill comes, or tip the wait person. In any case, you're waiting for me, and I take off in my spaceship. So the first thing you see happen is that when my spaceship accelerates, my vector, the red vector, rotates in 4-dimensional space-time until I achieve a speed through space of 91% the speed of light. That occurs when my vector makes about a 25-degree angle with your space axis, in this case your x-axis. So you can see that rotation here. Remember, I said you're always moving at the speed of light through space-time? Well, that remains true, as you can see here. Both of our vectors remain the same length in four-dimensional space-time, regardless of which way they are pointing or are rotated. Your vector is still pointed fully in the time direction, whereas my vector has now rotated in four-dimensional space-time, and it points at a different angle. Remember that each vector always has a value of 186,000 miles per second, which is the speed of light. But now, here's where things get interesting. To make things easier, let's superimpose my coordinate system on yours and look at what happens to measurements of time, distance, and mass with me moving at 91% the speed of light. Okay, there it is. So now we've got superimposed coordinate systems, mine on top of yours. Let's see what interesting things happen next. So here we go. My spaceship is going 91% the speed of light, and there's a whole bunch of stuff going on here. We're going to start with time dilation. To begin with, we note that the projections of my red vector right here on your space axis is about 0.91. It's like a shadow, 0.91. That means I am moving at 91% the speed of light, okay? Second, we look at the projection of my red vector or component or the shadow on your time axis. That comes out to be 0.42. So what that actually means is that for every 1 second that passes on your clock or watch, only 0.42 seconds pass for me in my spaceship. That also means that for every second that passes for me, 2.4 seconds pass for you. It also means that for every year that passes for me, 2.4 years pass for you. So sorry, but you are now aging faster than I am because of my high-speed motion in the spaceship. If I go faster, even closer to the speed of light, the effect even becomes more pronounced. Let's take a quick look at that. Here we're going 99.999999% the speed of light. And my vector is rotated way down here now. So that means that in this case, the projection on the time axis is such that for every second that passes for you, only 0.00014 seconds pass for me in my high-speed spaceship. This is what they call time dilation. When I return to Earth from my high-speed round-trip travel at 99.999999% the speed of light, about 7,142 years will have passed on Earth to just 1 year for me. Sadly, you won't be around anymore to be sitting at the table waiting for me or won't even be alive. So that's what time dilation is all about. Remember, we are always moving at the speed of light through space-time, and that the faster I move through space, the slower I move through time, and when moving through three-dimensional space, I lose or trade off some of my motion through time for motion through space. And vice versa. Now, let's take a quick look at what happens to the length of the spaceship that I'm in. Let's quickly go back to our table when we were at rest relative to each other, and we both agree that the length of my spaceship is 5 units long. Here's the back, here's the front, that's 5 units. But now let's look at how the length of my spaceship projects on your space axis when I'm moving at 91% the speed of light again. Note the blue dotted lines. One is the back of my ship, one is the front of my ship. You'll notice that right now, when you look at my ship, it only looks to be 42% as long as it used to be. In other words, instead of being 5 units long, it's now only 2.1 units long. Okay, that's called length contraction. And let's take a quick look if I can show you here. That's what the spaceship looks like at 91% the speed of light compared to when it's at rest. All right, now the next thing we're going to talk about briefly is called simultaneity. That is the things that seem to happen at the same time. Let's say we are sitting at the table again, and we have flash bulbs at the front and back of the room. If they both go off at the same time, we're in the middle of the room, we say they're simultaneous events. Okay, same thing here. Let's get into my spaceship. And in my spaceship, let's say I've got a flash bulb at the front of my ship and the back of my ship, represented by these bars. And I set the bulbs off at the same time, and I'm sitting in the middle. I see them go off at the same time, so they're simultaneously flashing. But that's not what you're going to see. Let's take a look at how my spaceship is rotated in four-dimensional space-time. It is rotated in four-dimensional space, and we'll see how the front and back of my spaceship now project on your time axis. As you can see, that while the bulbs flash for the same time for me, those events project on your time axis, shown by these green dotted lines, at two different times. So when I say that it happened at the same time, the two events happened at the same time, you say, no, it didn't. One event happened before the other. And this effect increases with speed. The last thing we need to talk about here is mass. What about mass? When the ship is moving, my spaceship is moving, we have to apply some E equals mc squared here, which means that energy is equivalent to mass. The faster my ship goes, it gains kinetic energy. And the more massive and the more kinetic energy it gains, the more massive it becomes. In our current example, at 91% of light speed, you measure the mass of my ship as about 2.38 times as massive than when at rest. That's simply 1 divided by 0.42 will give you 2.38. At 99% the speed of light, 99.999999% the speed of light, the mass of my spaceship will have increased to about 7,142 times its rest mass. The faster my spaceship goes through space, the more massive it becomes. And my spaceship, or anything with rest mass, can never reach or exceed the speed of light in the 3 dimensions of space, because as you get closer to the speed of light, the mass of objects approaches infinity, and that is shown by this graph. You can see the exponential curve and how it rises. So what this curve is showing us is that it would take an infinite amount of energy to accelerate an object, like a spaceship or anything with mass, rest mass, to reach the full speed of light when it's moving through space. So that means that the speed of light through space, 186,000 miles per second, is indeed the universal speed limit for anything in the universe, because we do not have an infinite amount of energy to input into something to make it get to the speed of light. So as you approach the speed of light, any energy that you input, the closer you get to light speed, it becomes mass rather than speed. I want to take one quick look at a light beam here, at a special case. This is going to be a light beam. And the light beam is special because the light beam is actually trapped in space, and it does not move through time. The light beam lies directly on the space axis and moves, yes, at the speed of light, but it only moves through 3-dimensional space. As you can see, the projection of the light beam on the time axis is 0. And so it does not move through time at all. As I said, it's trapped in space. If you could move through space at the speed of light, you would not age. It's a secret of living forever. However, as we discussed before, nothing with rest mass can be accelerated to the speed of light. Light has no rest mass, so it's special. We humans and spaceships and anything that you can like weigh on a scale, that has rest mass, you cannot accelerate to the speed of light. In space. In space-time, 4 dimensions, we're always moving at the speed of light, but you cannot get to the speed of light in space. You cannot get I cannot get my red vector to lay on that x-axis the way this light does. And there's still so much more to relativity, but I think we're really out of time here for our 15-minute presentation. So we presented some major consequences of Einstein's theory of special relativity. As a side note, this stuff is not just useless. In fact, our GPS system we depend so much on would become useless in a matter of a couple days if relativistic effects such as time dilation were not accounted for. The clocks on the satellites go at a different rate than the clocks on the ground do. So that's our 15-minute super fast description of the highlights of Einstein's special theory of relativity. In summary, you're always moving through 4-dimensional space-time at the speed of light, but how fast things move through time depends on how fast we're moving through 3-dimensional space and vice versa. So, again, if you would like a slower, more descriptive, but still conceptual understanding of special relativity, see my playlist for special relativity in less than an hour or so. And bye for now, and thanks so much for watching.